The radial-axial ring rolling machine is a specialized industrial equipment used to manufacture seamless rings from metal blanks. This machine employs both radial and axial forces to reduce the thickness and height of the ring while expanding its diameter. The process is essential in industries like aerospace, automotive, and energy, where large, high-strength rings are required. To illustrate the capabilities of the radial-axial ring rolling machine, let's explore two examples with specific dimensions and outcomes. A ring blank with an outer diameter of 1,677 millimeters, an inner diameter of 1,253 millimeters, a height of 3,999 millimeters, and a wall thickness of 212 millimeters is processed through the radial-axial ring rolling machine. The machine applies radial pressure to reduce the wall thickness from 212 millimeters to 173 millimeters, while simultaneously expanding the ring's outer diameter to 1,871 millimeters and its inner diameter to 1,525 millimeters. Outer diameter, 1,871 millimeters. Inner diameter, 1,525 millimeters. Height, 3,986 millimeters. Wall thickness, 173 millimeters. After rolling, the ring's outer diameter increases to 1,871 millimeters, the inner diameter to 1,525 millimeters, and the height slightly decreases to 3,986 millimeters, reflecting the material flow during the process. The slight reduction in height from 3,999 millimeters to 3,986 millimeters indicates a controlled compression in the axial direction. The rolling time for this process is recorded at 214 seconds, and the final weight of the ring is 27.6 tons. The rolling process not only changes the dimensions, but also enhances the material properties, improving the ring's strength and structural integrity. Outer diameter, 3,954 millimeters. Inner diameter, 1,584 millimeters. Height, 1,288 millimeters. Wall thickness, 1,185 millimeters. A much larger ring blank with an outer diameter of 3,954 millimeters, an inner diameter of 1,584 millimeters, a height of 1,288 millimeters, and a substantial wall thickness of 1,185 millimeters is subjected to the rolling process. This larger blank requires more extensive deformation, showcasing the machine's capability to handle significant material volumes. Outer diameter, 6,395 millimeters. Inner diameter, 5,264 millimeters. Height, 1,148 millimeters. Wall thickness, 566 millimeters. Post-rolling, the ring's outer diameter expands significantly to 6,395 millimeters, while the inner diameter grows to 5,264 millimeters. The height decreases to 1,148 millimeters, and the wall thickness is reduced to 566 millimeters, illustrating a substantial deformation. This transformation is achieved in 460 seconds, with the final product weighing an impressive 89.3 tons. The longer rolling time and increased weight reflect the greater complexity and effort required to process such a large ring. Hydraulic radial forging machines are advanced, high-performance equipment designed for precision shaping of metal ingots into various forms. These machines apply controlled radial force, enabling the production of complex, high-strength components with minimal material waste. Capable of handling diverse materials and large dimensions, they are crucial in industries requiring exacting standards, such as aerospace, transportation, and energy. The 18 meganewton press force ensures powerful and precise metal shaping. The 8-ton ingot capacity enables forging of massive, heavy components. The 130 millimeters smallest finished diameter ensures precision in fine component forging. The maximum forging length of 18 meters allows the production of exceptionally long components, making it ideal for industries requiring extended parts such as railway axles, energy plant shafts, and structural beams. This capability ensures that large-scale products can be forged in a single process, reducing the need for additional welding or assembly, thereby enhancing the structural integrity and performance of the finished product. Surface quality. The surface quality of a forged product is a key indicator of the overall precision and finish of the forging process. Hydraulic radial forging machines, like the SMX-type, are designed to deliver excellent surface quality by applying controlled, uniform pressure throughout the forging process. This minimizes surface imperfections such as scale, cracks, or irregularities, reducing the need for extensive post-processing and machining. Middle radius. The middle radius refers to the region within the cross-section of a forged component that lies between the surface and the centerline. Achieving uniform properties in this area is essential for ensuring the overall structural integrity of the part. Inconsistent grain flow or material defects within the middle radius can lead to weaknesses, particularly in components that must withstand significant mechanical stresses. Centerline. The centerline of a forged component is the central axis that runs along its length. Maintaining a defect-free and homogeneous centerline is critical for the mechanical strength and durability of the part. Any inconsistencies or imperfections in the centerline can act as stress concentrators, leading to potential failure under load. Kamihara Cast Steel Works, established in 1955 in Kochi Prefecture, is a leading manufacturer of cast steel products for ships, specializing in high-strength components like propeller bosses and rudder horns. The company is renowned for its advanced technology and quality, making it a key player in the maritime industry. In maritime engineering, the propeller and rudder are crucial components that significantly influence a vessel's performance and maneuverability. The propeller, often referred to as a screw in nautical terms, is responsible for propelling the ship forward by converting rotational motion into thrust. It is a key element in the propulsion system, typically mounted on the stern of the ship and driven by the engine through a shaft. Kamihara Cast Steel Works manufactures propeller bosses, which are large, heavy components that house the shaft passing through the propeller, ensuring its stable and effective operation. These bosses can weigh up to 17 tons, reflecting their importance and the high strength required to withstand operational stresses. The rudder, on the other hand, is vital for steering the vessel. It controls the direction of the ship by redirecting water flow, which creates a force that turns the vessel. The rudder is often supported by a rudder horn, which is a critical structural component. Kamihara Cast Steel Works produces these rudder horns, which are robust enough to support the weight and stress exerted during navigation. Weighing up to 4 tons, these horns are integral in maintaining the effectiveness and reliability of the steering system. Heating. The carbon steel is placed in a furnace and gradually heated to around 1,000 degrees Celsius. This process ensures the steel reaches the required temperature for optimal forging, making it malleable and easier to shape during subsequent manufacturing steps. Material cutting. The carbon steel is carefully cut to the specified dimensions and shapes needed for the overpack components. This involves precision cutting techniques, often using saws or lasers, to ensure the pieces match exact requirements. Proper cutting is crucial to avoid material waste and ensure that the components fit together accurately during the assembly and welding stages. Body formation. A cylindrical shape is formed from the cut carbon steel pieces. This involves techniques like rolling and shaping under controlled conditions to achieve the desired diameter and length. The cylinder must meet precise specifications to ensure structural integrity and proper fit during later assembly and welding processes. Apply pressure using a 2,000-ton press. Thickness adjustment. Apply pressure to the cylinder using a press to uniformly adjust and achieve the required thickness throughout the body. Carefully modify the end sections of the cylindrical body to ensure they meet precise specifications. This may involve trimming or reshaping to achieve the correct dimensions and fit. After the final shaping, the forging process is complete. The hot forged body is then allowed to cool naturally at room temperature. This slow cooling process helps to relieve internal stresses and ensures the material retains its strength and structural integrity, essential for the subsequent machining and assembly stages. Refine the end sections of the cylindrical body to ensure precise alignment and fit. This involves techniques like milling or grinding to achieve the required dimensions and surface finish. Perform detailed machining operations on the forged body to achieve exact specifications. This includes turning, drilling, and milling to create precise features and smooth surfaces. Secure the body onto a lathe for further processing. Machine the interior surfaces of the body for proper fit and functionality. Finalize the body, ensuring it meets all specifications and weighs about 5.1 tons. Machine the lid to the required dimensions. Finalize the lid, ensuring it weighs approximately 300 kilograms and fits precisely with the body. Clean and inspect the mating surfaces of the body and lid to ensure they are free from contaminants and properly aligned. This includes removing any rust, dirt, or oil and ensuring the edges are smooth for a strong weld. Set up the TIG welding equipment and adjust the settings according to the material thickness and welding specifications. Position the body and lid securely to prevent movement during welding. Begin TIG welding at a depth of 19 centimeters, carefully controlling the weld bead's placement and penetration. Maintain a consistent welding speed of 6 to 10 centimeters per minute while rotating the piece to ensure an even weld. Continue welding until reaching a depth of 2 centimeters from the surface, ensuring complete fusion and strength. Kaltek, based in South Korea, is a leading manufacturer of specialized industrial machinery, including ring rolling machines, hydraulic presses, and manipulators. Among their flagship products is the full automatic ring rolling machine, which stands out for its advanced automation capabilities and precision engineering. Kaltek's full automatic ring rolling machine is designed to streamline the entire ring rolling process, offering an all-in-one solution that ensures efficiency and consistency. The machine automates every stage of the ring rolling process, including approaching, rolling, and return operations. This full automation not only reduces the need for manual intervention, but also enhances productivity by minimizing downtime and maximizing output. The machine's automated approach function optimally positions the workpiece before the rolling begins, ensuring accurate alignment and reducing material waste. During the rolling process, the machine precisely controls the force and speed to achieve the desired ring dimensions with high accuracy. The automated return function then efficiently repositions the workpiece or readies the machine for the next cycle, further enhancing the overall process efficiency. Kaltek's ring rolling machines are engineered for durability and long-term performance, making them a reliable choice for industries requiring high-precision rolled rings, automotive, aerospace, and heavy machinery. The integration of advanced control systems allows for easy monitoring and adjustment, ensuring that the production process remains flexible and adaptable to varying requirements. The steelmaking process begins with the extraction of taconite, a low-grade iron ore from the earth. Taconite is a sedimentary rock that contains iron within its structure. To access the iron, the rock is first blasted and then ground into a fine powder. This powder undergoes magnetic separation to extract the crude iron ore from the non-magnetic waste material. The extracted iron ore is then formed into marble-sized pellets through a pelletizing process. These pellets serve as the primary raw material for iron production. In addition to iron ore, the process also requires coke, a high-carbon fuel derived from bituminous coal. The coal is crushed and then heated in airtight ovens for 12 to 16 hours, driving off impurities and leaving behind solid carbon fuel. This coke is essential for generating the high temperatures needed in the blast furnace to melt the iron ore. The stage takes place in the blast furnace, where the iron ore pellets and coke are combined with limestone, which acts as a flux to remove impurities from the molten iron. The furnace is continuously fed with a blast of superheated air, causing the coke to combust and produce the intense heat required to melt the raw materials. This process converts the iron ore into molten iron, sometimes producing more than 90,000 tons of it per day at U.S. Steel's largest facilities. The molten iron, which reaches temperatures of around 2,700 degrees Fahrenheit, is tapped from the furnace and transported in giant submarine ladles to the next stage of the process. In the basic oxygen furnace, BOF, molten iron is transformed into steel. The process begins by adding recycled steel scrap to the furnace, followed by the molten iron from the blast furnace. High-purity oxygen is then blown into the mixture at supersonic speeds, which oxidizes impurities and converts the molten iron into steel. This stage is fast-paced, with up to 250 tons of steel being produced in less than 45 minutes. The oxygen blowing process also generates intense heat and sparks, which makes the steelmaking process visually spectacular. After the steel has been refined, it is ready to be cast into semi-finished shapes. This process involves pouring the molten steel into a tundish, a large funnel-like structure that feeds the steel into continuous casting molds. As the steel moves through the molds, it cools and solidifies into shapes such as slabs, billets, or blooms. The temperature of the steel at this stage is around 3,000 degrees Fahrenheit. Most U.S. steel plants focus on producing sheet products, so the continuous casters typically produce slabs, which are then cut into sections up to 40 feet long. These slabs are stacked and set aside to await further processing in the hot strip mill. The hot strip mill is where the steel slabs are transformed into thinner steel sheets. The slabs are reheated to approximately 2,400 degrees Fahrenheit, then descaled to remove any surface imperfections. They are then passed through a series of roughing stands, which reduce their thickness and increase their length. After roughing, the steel passes through finishing stands, where it is rolled even thinner. The final product is a steel sheet that is often only fractions of an inch thick, but can be thousands of feet long. These sheets are then cooled and rolled into coils. The steel coils may undergo several finishing processes depending on their intended application. The first step is usually pickling, where the coils are passed through an acid bath to clean the surface. Some coils are then cold rolled to further reduce their thickness and improve their surface finish. Other finishing processes include coating to prevent corrosion, tinning to apply a thin layer of tin for products like canned goods, annealing to make the steel more malleable, and tempering to increase hardness and create specific surface textures.